So this is the robot for Science Olympiad robot arm. It's one of the events. It's 2016, so they cycle through the events, they change things up. The robot I can break up into 4 major pieces. This is kind of a minor 5th piece. These originally were a brace on the top here where the rubber band connected, but it broke off while I was packing it. It actually was fine for the competition. I'll fix that later. I've just reattached the rubber band up there. So we have the robot arm itself, the base that the robot arm attaches to. This is most of the control. This is like the hub, and this is the remote. And this is another minor part of the remote. This is just for the claw. I had the choice between making the claw a DC motor or a servo motor. I found out it definitely needs to be a servo motor, but I'll tell why later. This is a DC motor, so I just switched between open and close. Had I done a servo motor, I would have put a potentiometer on this remote so that I could twist the claw open, twist the claw closed. There's a lot of long wires here. If you look at the wires that are power wires, I twisted them together. I don't know if it'll focus on that. Power is running through these, and I twisted them. Versus if you look at this one, for example, or any of the servo ones, I kept the signal wire separate, and the reason is the twisting is supposed to cancel out the magnetic fields created by the power wires, so they don't interfere with the signal. Of course, there'll be a little when you do this. The only way you could really eliminate it is with a coaxial cable. Which I'm not going to do that for this. That'd be way too expensive. I don't even know if they exist for small applications like this. The reason they're colorful, thin, and I have so many of them is the school was redoing their Ethernet cables throughout the entire school. They just threw them in the trash. It was like a mile worth of them, and me and my friend just cut them in half and said, you take half, I take half, and now I have a ton of Ethernet cable. I will never run out. It's literally like 5 pounds of Ethernet cable. This switch, I could pry it open with a screwdriver. I can't really get inside. It has 3 positions. I originally wanted to make it so it was off, close the claw, and open the claw. But the problem was I just couldn't configure it that way. The only way I could figure out to configure it is close, open, and off. So when I would go for objects, I would line the robot arm with the object, close the claw, and then once it was closed on that object, I'd whip it back to off without hitting the open setting. And then, when I wanted to open it, I just open and go back. I labeled the switch. I have my wires labeled. Light green was ground, dark green was power. Blue and white I didn't really worry about. Technically there is a power and a ground for them, but I just wire them up with the DC motor. Okay, I'm going to start with the electrical, going through all the electrical stuff. I'll actually unplug it while I'm doing this. I didn't have a real on or off switch, I just kind of plug it in and unplug it. I used to do the ground, unplug and unplug the ground. I never really remembered why, but I know there's a good convention, always unplug the ground or something. I think in DC circuits it really doesn't matter as much. But my red one was breaking apart. It burned out at one point because the current through here was so high. It gets hot, remelted my hot glue. I didn't really care. I just soldered it back together and hoped it wouldn't do it again. Hasn't done it again. I have thicker wires if I wanted. So this is an 11.1 volt battery, 2,200 milliamp hours, rechargeable. Goes to these 2 things, alligator clips. Gets divided by parallel voltage regulators. I'll just show you the voltages. This one powers the servos. This one powers the Arduino. Okay. The servos I keep around 7 or 7.2. Higher than 7.2 they may burn out. I have not yet burned out a servo, but I saw on the reviews that it will burn them out, so I just don't do it. Arduino runs off of 5 volts. It has its own voltage regulator. These are voltage regulators. I don't know if I said that or not. They're switching voltage regulators. Some voltage regulators will just kind of burn off the extra energy, and as heat they'll just resist. These, I'm not 100% sure, but I've heard they switch on and off very quickly to regulate the voltage you want, kind of like pulse width modulation on the Arduino, but I don't know if it's exact. It's not, probably not the same. This wire goes to Arduino. And the Arduino needs at least 1 volt higher in order to do the drop. You have to do a higher voltage to do the drop. If you do a 5 volt to a 5 volt, it'll take off more and it just won't do it right. So this one goes straight into this rail. This rail has powers and grounds that go to each of the servos, and then the signals from the Arduino go to those servos to tell the servos where to go. I powered the potentiometers with the 5 volts from the Arduino. That's in this rail, so you have the potentiometers. And this is the signals that get sent by the potentiometers. I think that's it for electronic. Oh, well, the program I just kind of copied and pasted from one of the sample programs. There are 4 lines, so I had the option to do 4 servos. The 4th one would have been the claw, but I ended up not doing it, so there's a 4th line that just kind of sits empty. I guess I'll move over. Here is where I use potentiometers. Potentiometers will get some, they're variable resistance, and depending on what the resistance is, it will send a signal to the Arduino. The Arduino will interpret that signal and send a position to the robot arm. Now this is the main controlling area. I'll show that in a few minutes. These just sit here and do nothing. They were backups. When I was building the robot arm, I had a couple potentiometers burn out on me. These never burned out or got hot. But in case something did happen in my competition, I had these as backups, which I would just rip off and plug in. So I'm going to go through the main part of the robot arm from the bottom up. The rule was it had to fit within a 30 centimeter by 30 centimeter area, so I just cut a 30 centimeter square base. This is the front, this is the back. I bought cheap servos from China, $10. They were pretty strong. I'm going to find one in the box. The only problem was they didn't have full 180 degree motion. So it has a little thing just to support on the back and the main servo part there. This is the servo horn it came with. One goes on the main part that turns. One is just kind of a free moving one as an extra support. Screw, keep it on there, another screw on that end. If anybody wants to see what the label is, that's what they were. They were pretty good servos. Not exactly 180 degrees like they claim.
What's a 180 degree servo?
Well,
it turns 180 degrees?
Yeah, it turns 180 degrees. There are 90 degree servos, 360 degree servos. More industrial robots will have, they're just like motors that tell position. But they'll keep spinning. Okay. These are hobby servos, and they use gears to stop where they want to stop. Now, one of the problems I had with, I basically jammed this onto the servo, cut it out. It was a Vex gear. Jammed it on there and made my own servo horn as a gear. It stripped. I originally had these plastic ones on the servos there. They stripped. I ended up missing a whole competition because they stripped. I just couldn't compete. Bought these off eBay. They weren't that expensive. Nice pretty blue. Drilled some holes on that. Made it so that it can move that now. It's now got more support. And I like these because they're adjustable size and they can get very tight. I put one on there. I ended up just chopping that off and putting a lot of glue. I meant to put that metal bracket on the inside so it would have more support. It just didn't work out that easy. But had I had more time, I would have made it better supported. Now back to, I want to go back to the base. I put these blocks on so that I could, support it and have the chain run underneath. And the reason for the gear and the chain is because the servos weren't 180 degrees. I ended up using a gear ratio. I lose some mechanical advantage, so the servo is weaker than it would normally be, but I got a wider range of motion. It ends up being able to go from about there to there. It was slightly over 180 degrees, but about 180 degrees. I was afraid the chain would break. Never broke. I was afraid there would be friction of the plastic rubbing. Doesn't look like there's much. Ordinarily, I would have just tightened the chain together, so it would just be in tension, so there's no whiplash. I don't know what it's. I forget what it's called. There's some special name for it. But I couldn't figure it out, so I couldn't get them tight enough, or I was afraid I would break them, so I ended up putting that in. There's still some play in it. It's a little annoying. I ended up making this thing to hold the gear myself. My tech teacher let me use some of these gears. I know Vex parts are kind of expensive. I didn't want to use too many. So this attaches on to there. Oh, I'll let you see the bottom. I bought this turntable from McMaster Car. Miss McMaster Car. I don't remember what it was called. It was an industrial website my tech teacher showed to me. This was a plastic one. They have metal ones. They have all kinds of stuff. It was pretty cool to see. Pretty minimal friction, and I needed less friction because this was this servo losing its mechanical advantage. It was having trouble turning, so less friction, always nice. So I just figure out how to put that on there. Turns on there. Now moving up, I had the turntable, which I lightly hot glued to a PVC pipe. This wasn't a whole pipe, this was an end cap. I found some scrap wood, just drilled the scrap wood to the PVC pipe. Also, you'll see that the gear, there's another gear on the bottom that makes this turn, one of these Vex gears that fits with the square things. I ended up just screwing in the gear to the bottom. In order to attach the servos, I just cut these blocks, and if you want to go around, you can see where I just drilled into the blocks with some other screws. A lot of it's wood glued together. Wood glue is pretty strong. Now I still have one of the plastic turners on there because it can't strip. It was never geared in the first place. It just kind of supports some of the stress. This is the geared side with the anodized aluminum servo horn. These screws were just random screws, wood screws I had. I put some glue on the caps because it was annoying to get poked by them. I had to do some weird stuff with the screws on there, drilled some holes in that aluminum piece there. It was hard to make that support. Now I have some stuff to show, which is in this box. These were my backup potentiometers. Were potentiometers I was using, just some random nuts and bolts, Loctite in case any vibrations knocked things loose. Before I had the turntable, I was going to try and make a flat piece and use these wheels, but then my tech teacher showed me the turntable and that was much better. backup chain in case anything broke. More servo horns, random stuff. But this was really nice. I found this on eBay. They were, I think, M3 screws. They're the same screws that go in the tops of these. If you want to move there, they go in. They fit into the servo horn spots. So that was really nice. They're also the screws that. No, so they fit. I didn't mean to say servo horn. They fit into the servo screw hole there, and then they also fit in the blue servo horns themselves. They're the same screw. And you can see I used them in random places on the robot sometimes if I just needed some supports and screws to bolt things together. When I bought the kit, it came with nuts, bolts, all kinds of sizes of bolts, these 2 screwdrivers or Allen wrenches. I threw in I found some little washers that helped me. It did not come with those little washers. Those are some of my leftover screws from one of the servos. Ended up stripping. Well, okay, so that black screw goes to this servo because I ended up not using its screw. And then on this servo, I stripped the plastic for that support one. But I didn't even need the screw anyway. There's enough tension between here, if you zoom out a little. There's enough tension holding this together that I didn't need that screw to hold it on. So attach that. I cut these pieces to lengths that I wanted. Glued these bracket sort of things to keep it together. I had a lot of problem with tipping and friction. You know, if I put a lot of friction on one side, it's still too much for the turntable. This ended up reducing a lot. The weight it's far enough out that it can counter this. I can move it pretty freely. With the remote, it can move under that servo. Like I said, I want to keep a lot of stress off this servo. But it also works, it's close enough in that it's just nice to spin when it's close. I ended up bolting it so it wasn't going to move so much. I generally take it off when I'm moving the robot because it might snap this support back here. The servos are pretty strong, but this is a lot of weight, especially with this heavy steel claw. I didn't mean to use this claw, it was more of a last minute thing. I was running out of time and I just took a Vex claw from the classroom. I got permission. I bought a new one, gave it to them so I could keep the Vex claw. It was my dad's idea to get these long poles and take off some of the stress with, you know, bungee cords. Originally I wanted to use bungee cords and he told me I should make these poles to support some of the stress. So this one was done over twice. One of the things broke. Hopefully it'll still lift, I don't know. This one was done once. This one obviously has to support a lot more than this one. I attached it on my brackets. So I have this other servo I made. Took a long piece of wood, cut the 2 blocks, screwed it into the blocks. That was my servo mount. And then I also screwed in the servo with some wood screws. You might want to zoom out. That's not a very good... People can't see that. Zoom out more. Nobody's going to see that. Yeah, alright, thank you. Into the brackets. Here, I was just kind of at a dilemma of how am I going to attach this. Just took 2 blocks, some screws, and just kind of jimmied it together. This is only out here because I was afraid of cutting too much and not having enough length. Figured if I have extra, who cares? I put it diagonal. Some people make their wrists. You should zoom out more. if you zoom in super close, people aren't going to know what they're looking at. So some people will make the wrists move up and down. Some people will even go so as far as to make them move the yawl or something. I just put it diagonal. It was good enough for picking things up. It could get things far away. It could get things up close. So that worked out fine. So this is the 11.1 volt battery I bought. I bought the battery before the charger. When everything's hooked up, it lasts a bit. Not a super long time. It's not like an RC toy where you can drive it around for a while. I mean, you'll get, I'll say 10 minutes, but that'd probably be high. The competition's only 3 minutes, so I don't have to worry. I should probably buy another battery just for when I have it. They can charge pretty quickly. So it plugs in here. It's a 3-cell pack. Plugs into the 3-cell charging spot. They say DC input, AC input, and the DC input, it works when there's nothing on the AC input. But if you have AC on and you try and connect something to the DC, now I mean it seems silly to have 2 inputs, but the DC input will be an output. It will start outputting power. And this was not my first charger. This is my second charger. I fried the first one by I don't remember. It was something with this DC input. It scares me. I just don't use it because it's too risky. I think they should have something to protect against that. You know, if you're gonna get a $40 charger and have some, I think they should have a circuit that protects that if you have one plugged in, the other should not be running. I've done some circuit stuff, digital electronics. Nothing. I don't think we've done anything like that, but I don't think it's a very hard safety thing to put in. It's got different. You can switch between lithium polymer batteries, which is what I have, and lithium ferrite. I'm not sure, something iron. You know. So I use lithium polymer. Is it polymer? Lipo. Whatever. There's an interface switch. It'll tell you what you're charging, what their milliamp hours, amperage. I never really use that. All I ever really use is have it on this LiPo screen, and I can increase the current. If I really want a really quick charge, I'll do 1 amp. Normally I just keep it at the 0.1 amps if I'm just gonna like leave it overnight. Alright, so the claw is spring-loaded to be closed, so it'll sound like it's having more trouble opening than it does closing. This is so when you close it, you can turn off the power and it'll hold whatever you want it to hold. So, close, open, off, open, close. I'll explain why that happens later. I'm not trying to tell it to do any of that. It went back to the position it was supposed to be in, but when controlling the claw, messed with some of the circuitry, and bad stuff happened. I'll explain that. Now just controlling it, if I move it, it's kind of like, it's supposed to be like the arm. That if I move this, it's jammed for some reason. So it might be losing power. That servo may not come back up when I bring it down to show it, but it's like the robot. It's supposed to mimic the arm. The proportions of angles are not right, but basically when I bring it all the way down, it's all the way down. I can twist it side to side. And I can go down and up. So I can can control all this stuff. And it's going to get stuck there. So, I think this is the last thing I have to talk about. Well, two things. One's a minor thing, which is this servo. This servo is cool. Nothing's wrong with it. This servo is cool. This servo is under a lot of stress. I've had a lot of fear of it burning out. I can't even keep my finger on it. I think the first thing to go would probably be the potentiometer. There's a potentiometer inside each servo. That's how it knows what position to be at. The gears are connected to the potentiometer. The gears are also connected to the motor. The motor could burn out, but whatever burns out, it's going to suck either way because I can't replace it. I've thought maybe I could put a heat sink on it. It's not a very good thing to put a heat sink on because there's nothing really to mount it to. I could get some thermal paste from when I did my processor on my computer. Just duct tape a heat sink on it. I have some extra heat sinks. I have one that might be small enough. I'm not really going to be doing this project again. Maybe I'll do it so the next kid can have it. Now, as I was talking about before, as to why I should use a DC motor instead of a servo motor, and why it was causing my arm to fling all over the place when I opened and closed it, is so if anyone is watching this and they've been in an electricity and magnetism class, they might know this is so motors use inductance and Faraday's law and not Faraday's, Lenz's law in the circuitry. So when you have the force going, spinning the motor, it creates a back EMF, because when you induct in something, it wants to restore the change by Lenz's law. Part of that restoring with a moving motor in a magnetic field is it will create a back current while it's moving in order to restore the change, to go back to a neutral position. That's why motors act as resistors, is because of that back EMF. If you take away the back EMF, well, it's not, you can't take away the back EMF. If you theoretically could, an EMF is electromotive force, voltage. If you took away that, it would just be a wire. There would be no resistance. Now what happens is when my motor is moving, you know, it has a current draw, but especially when it hits the ends, like the far side or fully open or fully closed, the motor stops spinning. If the motor can't spin, it can't create the back EMF. If there's no back EMF, there's no resistance. There's no resistance, there's full current. Full current's bad. It could burn out the motor, except that hasn't happened. The biggest problem is all the current is going through this motor. Now if you look down here, that motor is connected to the 5-volt power line from the Arduino that is also connected to all the potentiometers. If this is drawing all the current because there's no resistance, I mean it's going to take the path of least resistance, it's going to ignore all my potentiometers over here. It's just going to go ignore them completely. If these read no current, it means there's going to be, they think they're at full resistance. Now they don't think, but they'll send a signal of full resistance, which will go back to the Arduino. The Arduino will tell the servos it's at full resistance, go to the full resistance position. So that's why when you saw my claw go, the robot arm just flung itself forward, and as soon as I turned off the claw, it went back to its normal position. The reason one thing I could have done to fix this is pretty obvious. I could have put it on the same line as the servo power. It might cut out the servos, I'm not sure. I never tested it. Probably would have been better than completely cutting away the power from my remote, because the remote is kind of vital. But then if I can't turn the servos, well, that's just as bad. What I think would have been better is to replace the DC motor with a servo, because servos aren't always using power. If the potentiometer in the servo moves slightly out of position, the potentiometer will say, hey, I'm out of position. It'll spin the DC motor inside the servo and move back to position. Now, I'm not actually an expert on servos, so I don't want to mislead anyone, but I'm pretty sure that's how it works. So yeah, simple solution. Replace that with a servo motor. There is one thing I forgot to mention that would have made another problem. So two major problems: the DC motor and the length of the robot. I only had to make it have a range of 70 centimeters, a little more Pythagorean theorem, reach the corners, about 70 centimeters. This, I think, total, I don't have a measuring tape, I'd show you, wait, I might have a measuring tape. No, I don't have a measuring tape. Was about 90 centimeters, I think. It's a lot of extra length I don't need. It would have made the stress a lot easier on these the torques would be smaller. So it would have decreased the moment of inertia, so it would have made it, if I'm all the way out here, would have been exponentially easier to move, because mr squared for moment of inertia, I think that's the right formula. If I decrease the radius, you know, or as the radius increases, it becomes exponentially harder to move. Inertia stuff. And for torque, mass times radius. I hope I'm getting my formulas right. I don't have them in front of me. So, you know, it just would have been easier. Not exponential, but easier on these torques here. So that's all.